Welcome back, and in this lecture I want to continue the topic of the upper bound lemma and give you the proof of it. So remember the upper bound lemma is written as follows. So this was the upper bound lemma, which is the same saying that for any mu in ZP 0, 1 probability distribution and any n in n, the total variation distance to the uniform is at most a half of the square root of the sum k in ZP, k not equal to 0, of the Fourier transform of k to the power 2n. So that's the statement of the upper bound lemma. So let's prove this now. So just to remind yourself before going into the proof of all the statements, what is the L1 identity, what is the Cauchy-Schwarz inequality, what is the convolution theorem and the Plancherel's theorem, because all these four things are the main components of this proof. So so let's take the first step is the L1 distance gives, or maybe the L1, let's call it L1 identity, gives that if you take the total variation distance, we get this equal to a half of the square root of, not the square root, the sum of t in ZP of the mu star n t minus lambda t. That's the L1 identity. And now if we move the terms to the other side to make this a bit more clear and raise it to the power 2, so this gives you that if you take 4 times the distance of this thing to the square, so I'm actually taking the 2 to the other side, we get that this is just equal to this t in ZP mu star n t minus lambda t and this whole thing square. Okay, and now what we want to do is that we want to add and replace some functions and then try to get the Cauchy-Schwarz inequality into play. So we want to somehow estimate this. So we want to do an estimate this using a Cauchy-Schwarz inequality. So we want to find the right functions to do this. So there are a couple of ways to do this, and you can either use it for the constant function 1 or then using the way I'm doing it in here. So what I'm going to do is that we see that if you open this up, you write this, you get the p squared here, and then you get t in ZP, and you have lambda t, and then you have the mu star n t minus lambda t. I'm just writing it in this form, so I didn't do anything except I just take the p, because remember that lambda t is equal to 1 over p. So this is the uniform distribution in the group. So that's why I'm taking it inside and out and have this expression in this form. And now what I see here is that this actually, what I have here is that this is equal to p squared, and then you have what you have here is an inner product of two functions squared. So you have f and g, and their inner product. And what are the functions now here? So the for f, t is just equal to the lambda t by definition, and then gt, so this is equal to t in ZP, that's the function over here, and the gt is actually this an absolute value here, minus lambda t. And notice that this is a real value, so it has the complex conjugate of this is just equal to itself. So that's why we have this expression, this is actually equal to, by definition, the inner product. So that's what I have now here. And now what I can do is that I can use the Cauchy-Schwarz inequality. So Cauchy-Schwarz inequality for f and g gives that this expression here, maybe I can take like a red color, that's the Cauchy-Schwarz is being used here, so this is the Cauchy-Schwarz. So this is p squared, and now I can just put the L2 norms of here. These are actually squared because there's a square outside, so that's the L2 norms. And that's the Cauchy-Schwarz inequality that I'm using. So if I first use the L1 identity to give you this expression, so I have this 4 times t squared, and then I have this expression already in upper bound for this these statements. And now if you compute this, you can get that, okay, so this is p squared, and now let's compute the L2 norms, the first one. Then we actually get here, if we open this up, maybe I move it actually a little bit down here so we see the expression. So this is just equal to by the definition of L2 norm, this is equal to the sum of ft squared t in zp. But then ft was just lambda t, which is actually 1 over p. So this is just t in zp of 1 over p squared, which is then, if you open this up, this is p elements inside here. So this is just 1 over p. That's the first expression. So what we have here is that we have 1 over p, this whole thing, this is with the square, this is equal to 1 over p, and then we have the g norm here still, which is now equal to p square, this is p times g 2. That's what we have obtained. Okay, so what we have proved is that we can use this function g, which is this function over here, as an upper bound for the thing. So we have now an L2 norm existing here. So now this is kind of like a point where now the Plancherel's theorem might be something that I'd like to express. So let's first of all take this expression here, so this p squared. So we have now p squared, and I open this up a little bit, and what we see is that this is just a summation of t in zp of mu star n of t minus lambda t. That's by the definition of this. But actually, if you open this up, I'm just actually rewriting the same thing. I'm not doing anything fancy here. But what I'm actually doing, that this is actually equal to, this is like a function of the mu star n minus lambda. So that's the L2 norm of this. I mean, this is equal to the function g, but not exactly, because it's not the absolute values now outside. So this is not the same function g. G is a positive function that I have over here, but this is actually equal to the L2 norm of this. So that's the equality. And now Plancherel's theorem gives the following, that this is equal to, so this is the Plancherel. Remember the Plancherel was saying that there is like if you have a p square, so this is in this case you have a p here. Actually, sorry, there shouldn't be a square, because the p cancelled out, so there's no square here. So that now you have the p over here. So the Plancherel's theorem is saying that this p disappears. So what you have here is that you have the Fourier series n minus lambda, and you take its whole Fourier transform. So that's the Plancherel's theorem now being used. So we just take the Fourier transform and its square, and we get this expression at this way. If you would take the square root of the both sides, you would get the 1 over the square root of p, which was the statement of the Plancherel's theorem with the L2 norms. And now we can use the Fourier transform that is linear, in the sense that you can actually open this up as the Fourier transform of this one and minus the Fourier transform of the Lebesgue measure. We have this squared. And now if you open this up, this by definition is k in zp, and then you have the mu star n of k minus lambda k, and you have this whole expression squared over here. That's the definition of the thing. So we have this absolute value here and absolute value over here. Okay, and now if you look at this expression over here that we have seen, is that we started from, where did we start from? We started from like this total variation distance squared. We used the L1 identity to get it into this L2 norms, or this kind of inner products. And we used the Cauchy-Schwarz inequality to go to the L2 norm. And then we used the Plancherel's theorem to go into the Fourier side, and we ended up to this type of an expression. Remember that there's a 4 and a square in the outside, so once you take a square root at the end and divide by 4, we are getting the kind of statement. So now the final step is to now, there's one thing missing, which is the convolution theorem. So what we can use is now the finally is the convolution theorem. But before we apply that, let's look at these expressions what we see inside here, and we have the sum in over k in zp. So we have the elements that are, we are summing over the k in ZP. So we have, if you remember the upper bound lemma, we have those points which are non-zero, and then we have the zero cases. So let's look at the, in this sum, the cases where k is equal to 0 and when it's not equal to 0. So first of all, we see that if you take this Fourier transform of the uniform distribution, then we already did this earlier, that this is equal to when k is equal to 0, then this is it's just equal to 1, and when k is not equal to 0. And then on the other hand, we have that as this self-convolution of n, I haven't yet used the convolution theorem, as just saying that this is a probability distribution. We have that this mu star n Fourier transform at 0 is equal to 1. That's the, when you take any probability distribution, the Fourier transform at 0 is always equal to 1. And then also by the convolution theorem, we also have that if you take the Fourier transform at any other point at k, let's say for k not equal to 0, we have that this is by the becomes a product of these Fourier transforms to the power n. That's the convolution theorem at the point k. So now if you combine all these expressions and have this sum, and now we take this expression, then we can actually just study the whole sum. So let's take this arrow here into here. So this expression we have here, up here, we can now split it into sum. So we have now, first of all, when we have the case k is in ZP and k is not equal to 0, then when it's not equal to 0, we have that the Fourier transform of the uniform distribution is just 0. And then by the convolution theorem, we got this expression. So we have that this is equal to the Fourier transform at n. And then you have the rest. So you would have then at this point, oh wait, there's a square here. So there's a 2n here. And then you have the rest. So when k is equal to 0, you would just have the mu star and Fourier transform at 0 minus lambda at 0. But remember that this is just, this was equal to 1, and this was equal to 1. So then this is just equal to 0 as well. So you only are left with this expression k in ZP, k is not equal to 0, mu Fourier transform of k to n. So now we are like in business. So now we are in the expression that we have in the upper bound lemma. So if you remember them, all this is just inequalities and equalities. So if you go to the very beginning, we have this expression now. So let's take this expression here. So we have that the 4 times the self-convolution n lambda squared is at most equal to this sum k in ZP, k not equal to 0, the Fourier transform of k to the power 2n. So if you divide by 4 and take in square root, we have proven the upper bound lemma. So this is half and the square root of this expression. As claimed. So that's all we needed to do. So let's just go a little bit back to the proof. So what we actually did here. So just to highlight this is such an important result in the statement. So we start from L1 identity to transfer from the total variation distance, which was actually quite complicated expression, into these L1 norms, which are a bit simpler to understand. And then from the L1 norms, we go to using inner product with suitable functions and Cauchy-Schwarz inequality. We go to L2 norms. And then after you have dealt with the L2 norms, you would then go to the Plancherel's theorem, and that allows you to transfer in the L2 space into the Fourier side. And once you are in the Fourier side, you can then apply the convolution theorem to deal with the kind of the products you have at that stage, and you end up into this nice looking expression, which is the upper bound lemma. And In the coming lecture and in the next 2 lectures for this week, I will show you how to apply this for example, the mixing, ergodicity, and give you some examples of its applications and usefulness in the group ZP. And after that, we will then try to go to more general groups and see what are the analogs of these statements if you go beyond the cyclic group of P elements. So that's all for today, and I hope this was okay. Maybe I went quite maybe fast, but hope you got something out of this lecture. So that's all. Thanks.